we'll be able to finish the lecture today. So the logistics for this week is as follows. We have PA4 out already. PA4, you have to flip a picture. Okay. And then this Wednesday, tomorrow, we have a lab. Right, we have a lab tomorrow. The lab is mostly about the basics of so tomorrow is a lab 3, right? So we basically ask you to play with tuples a little bit, try to change the tuples and how to manipulate it. That's what you need to do. Okay. And then P4 is, like I said, is to flip pictures, flip a region in a picture. So be careful with off by one errors for that. So PA4 due this Sunday, lab due this Wednesday, tomorrow, and then this Friday we have a quiz. Okay. And this Friday will be the last quiz. Next week there's no quiz because we have the final. We have the final on Saturday of next week. Are there any questions folks have logistically for the class? All right. If anything come up, you can always ask. Okay. The plan for today is we'll be looking at background substitution and get started with steganography idea. And then on Thursday, we should be able to finish steganography. Okay. I think for the whole next week, what we may be doing is we may be just finish up everything on Tuesday and do a final exam review on Tuesday. And then Thursday is going to be QA, if I'm not mistaken. But we'll see how far we can go. Okay. Last time we were looking at processing a picture, like mirroring or flipping in a geometric way, right? So geometry is always confusing, and the best way for you to solve those geometric processing is to give yourself some examples and see, am I off by one or not? Am I including one extra column? Am I kind of missing out one column? Okay. So that's what you need to do. The next processing that we'll learn today is called background substitution. In other words, we want to change the background. Normally, when you have a nested for loop like what we did before, this is the structure, right? So for I in the range of some row range, for J in some column range, we basically specified a rectangular box, right? So this is basically start R. This is end R. Remember, end R is not included. So technically the last column is end R minus 1. This is this. Why do I write it over there? So this is start R. This is end R minus 1. This is start C. This is end C. Right, minus 1. So just be careful in here for range. So we basically specified a box, and then what we do is we will try to do something in this region. We can copy every pixel from this region to another spot using some sort of geometry. So we can mirror, we can flip, or we can say we'll filter out all the red, we'll change the RGB values in a certain way. So basically we say we will do something pretty uniformly in this region. We'll copy everything out, reduce every pixel's RGB value by a certain threshold, and etc. But what if the issue is like the shape we want to manipulate is irregular. It's not a box anymore. For example, this picture of a kid, and there's some red eye of the picture. I want to remove the red eye of the picture. And this region, as you can see, is not a rectangular shape. Or if you look at the one on the right side, I have this caterpillar. I say, hey, change the caterpillar from red to yellow, or from red to pink, whatever the color we want to have. And the caterpillar is not a rectangular shape. So how do we do it? How do we do it? This is where you say I specify a region that I want to manipulate, but you are not going to do the same thing for every pixel in that region. You want to say, I will observe a color, right? I will check the color of the pixel in this box. So I will look at every pixel's color in this box. If I see something red, I assume it's part of the caterpillar, and I'll just change it into whatever the color I want to change it into. For this red eye picture, you have to be very careful with this rectangular box you specify. You can't say I'll just go through the whole picture. Excuse me. If I go through the whole picture, what's going to happen is the red shirt of the kid is also going to be changed. So you may want to say, I want to limit myself to this box. So that's kind of the idea about background substitution. Okay. Any questions about this? All right. So you use nested for loop to give you some sort of box. And then in here, you can use the if statement to say, oh, if the RGB value is this thing, I will do something on it. Okay. One thing that we have to be careful is about color. When we have to judge on color, you have to be very careful. Let's do a quick vote. What do you think the color of this caterpillar is? What is the color? Let's vote in. Right. So a lot of us said A, right? The most popular choice is A, 25500. We're thinking is pure red, right? So let's go back to our lessons area. I think we have this picture available. Where is it? Week 4 Tuesday. Right, change the color. We do have this picture. I think it's caterpillar, right? I think I also have it. Let me download it. Save image as. Let's say save it on my test. For that. Let's open it up. Caterpillar. This is the picture, right? You can sample, but I open up using paint. Open with paint. And Paint has this sampler that you can sample the RGB values. So sample it here. If you look at the RGB, it's 25200. It's 25200. It's not 25500. Let's maybe there are other variations of red. Let's look at maybe that one is too dark. How about this red? This red is 25400. So human eyes really can't see these differences, right? So the takeaway message in here is, if you say I want to judge on the color, we should judge the color in a fuzzy way instead of saying it must be exactly 25500. We'll be in trouble if we do that because it doesn't specify the exact color in here. So let's try to change the caterpillar into yellow. What should I do? So what should I fill in? This first blank, second blank, and the last blank. So I say, I'll give you the image. This is the color I'm trying to change. And then X min, maybe I should change this into C min, C max, R min, R max. The min is included, the max is not included. Can you fill in these three blanks? Can you fill in these three blanks? If you are done filling in the blanks, give me a vote. All right, so a few of us are done. Okay, so if you're done filling in these blanks, vote in. All right, so let's work on this together, right? I, if you look at I is the row, right? So R is in the row min, row max, and J is the column, C min, C max. So the reason why that I is on rows is because of this part, right? It doesn't mean that the outer loop is always for row, although we prefer it, but it doesn't have to be. Okay. So I get the RGB value of this one. If it is close to this color, I would change it into yellow. So how do I determine if it's close enough? If I do this, if I say color 0 is the same as R and color 1 is the same as G, and color 2, right, while accessing the tuples, is the same as B. If this is the case, I change it into yellow. If this is what I'm doing, what do you think would happen? If this is the code I have, what do you think will happen here? If I try to pass in the caterpillar to it, let's vote in. What do you think will happen to the caterpillar? If this is the way I want to specify the color matching. You can vote in. So the votes are A, B, C, D in here. Okay. So I'll pass in this red, color as red as 25500, for example. All right, so I think we have a tie between A and C. Some of us believe the caterpillar will turn yellow. Some of us believe some of the pixels will turn yellow, but not the whole caterpillar. Let's try it. Okay. So this is the recolor function, right? Let's try it. So we say for I in range of, let me change the, this is Y is for row, right? Let's not use X and Y, we use column and the row. Excuse me. So for I in range of Rmin, Rmax, for J in range of Cmin, Cmax, we get RGB equals to image ij. And we have the if statement, right? If R is the same as color 0 and G equals to color 1 and B equals to color 2, we'll say image ij equals to 25500. So if I have a perfect red, I will change it into yellow. If I run the code, Python change.py, you do see in here, I read in the caterpillar. I'm going through the entire width and height of the caterpillar. If I see 25400, I pass in 254. If you look at new caterpillar, this is the old caterpillar. Do you see any differences? I think some of the pixels will be yellow, but it's so hard for us to see. I can't see it, but I'm pretty sure some of the pixels are changed into yellow, but I simply don't know where they are. So the caterpillar didn't change yellow. Right, so only some of the pixels changed into yellow. It's because of this exact match. Because just like what we said, the redness of the caterpillar is not pure red. There are some variations of red. So when you do color matching, it's better that you match it properly. Okay. So how do I match them properly? You can write a function. You can call this distance. You can say color 1, color 2. It will tell you how far away these two colors are. You can just return ABS color 1, 0, minus color 2, 0, plus ABS color. You know what? The best way to define the RGB is the redness is close enough, the blueness is close enough, and the greenness. So what's the best way? The easiest way is let's say this one would return a true and false. You know what? Let's not use this function. Let's just do it in here. So I would say ABS if R minus color 0 is less than, for example, 20. And G minus color 1 is less than 20. And B minus color 2 is less than 20. If this is the case, in other words, if RGB are pretty close to each other, then we'll change it into yellow. If you do something like this, the matching will be much better. Close the new caterpillar. So this is the old caterpillar. The new caterpillar is this one. Is it not changed? Maybe I have a typo somewhere in the code. Column, row. If RGB, oh sorry, my bad. I'm changing red into red, so it should be changing red into yellow. Okay. This is the caterpillar we have. This is a new caterpillar. Now it's yellow. Yeah. So the threshold of 20, if you look at the difference between them, is pretty subjective. You may say 20 is big or 20 is small. You just have to try it. Okay. So this is how you can change the color of something. Any question? All right. So given this function, how can I change Jenny's red, right? Because red eye, let's try it. So if instead of passing in caterpillar, I'll say Jenny red. And then I say if it's less than this, I change her eyes to be about brown eyes, 100, 100, 100. Instead of red eye. Change her eye color to be like a grayscale. Let's say this picture, I call this Jenny no red. Okay, let's try it. So I have Jenny red. This is Jenny no red. There's no difference at all. There's no difference at all. What's going on, right? So the picture, let me see. This is Jenny red. Jenny no red is this one. Let me out. You see these two pictures, they're almost identical. There's no change. I'm flipping in between these two. What's the reason? We are saying for this one, we say, oh, this is pure red, right? This is pure red. In fact, if you look at Jenny red, let me open up Jenny red in Paint. The red eyes, red color, if you look at it, let's sample it. If I sample it, this is the RGB value for her red eyes, 149, 54, 58. It's crazy. It's totally different. from 254.00. In other words, we are not even detecting the right color in here. So you got to be very careful. And I want to sample something like, for example, closer over there. 168.22.41. So in my code, instead of this one, I should say 164.22.41. Good. Let's check. 168. Okay. So 168. Maybe this would be good. Okay, let's try it. So make sure you detect the correct color. We have Jenny, no red. Let's close them because add stem doesn't automatically refresh. So Jenny red is here, Jenny no red. Hey, I think something changed. Right? If you compare this picture with this one, you see there are some gray stripes. And let's look at her eyes. Right? So maybe her eyes is also slightly different. This is Jenny red. If you look at this is red, no red. I think the eyes color, there are some grayscale in there, but unfortunately the shirt also got messed up a bit. Yeah, so but I can still see some gray stuff in her eyes in there. So how do I modify the region around her eye that is almost pure red? So one thing you can do is you can increase the tolerance on red color. So this one is like 60. And again, these values are try and fail. Okay. So let's check no red. All right, I think her eyes at least will look better now. Okay. This is her eyes. The redness are kind of, more of them are gone, but as you can see, the shirt is also messed up. We can fix the shirt later on, but let's take care of the eyes even better. So maybe 60 is, let's do 60 on all of them. And inadvertently, I may be too loose by defining what is a red color. But we'll see. This is Jenny, no red. Okay. Now I think I'm fine with this part. Okay. So if you look at her eyes are almost have no red in there, it's almost all brown now. But her shirt is not good. Yeah. In fact, her name is Jenny. She's the daughter of one of the CS faculty who is now at University of Michigan. Um, now, so her shirt got changed, but her eyes are good. Right? Her eyes are good now. Now, how do I avoid changing her shirt? We need to be more specific about this box that we create. Right now, I'm including the entire picture, but probably a better way is for me to just create this region around her eyes. That's it. So you can come here and let's look at the row information. And on the lower left corner of paint, you can see the coordinate of the pixel. For rows, let's see, is between 108, sorry, this part is 92 to 117. 92 to 117. This is the row information. So I should come here. For row is 92, 117. So instead of the entire height, this is the height I have. Similarly for the width, this is 111 to 200, for example. So again, these are ballpark numbers. Now, excuse me, I only specify the region around her eye. So when I run it, If you look at Jenny, no red. Her shirt should be preserved, but her eye colors are not black anymore. So this is her picture before. This is her picture after. Any questions about this? So the takeaway is, number one, you need to be careful about the box that you create. Number two is you have to be careful about the color you are looking for. When you say red, 99.9% of the time, we are not looking for pure red. We are looking for some sort of variation of red. So you got to be careful with this kind of fuzzy matching. ABS stands for absolute value. Okay. Are there any questions about this part? What does this mean in here? This is the bound for the rows. This is the bound for the columns. And we obtain it from by looking at the paint. If you look at the lower left corner of paint, as I move the cursor, they will start to change. I think the second number will tell you the row information. Row goes from 92, 118-ish. Column goes from 104 to about 200. That's how we obtained those values. Okay. And this dimension only works for Jenny Red. For example, it won't work for Caterpillar. Any other questions? All right. Yeah, go ahead.
How do you get rid of like the little shine in your eye that has like white in it?
Let's see. This one. Let me open it up in here. I mean, these things.
Yeah.
You just have to do it one more round. I think once you finish a majority of the eyes, and then you say, okay, how about this region? You just have to sample the color again, and you can call the function again to get rid of them. So the first round get rid of the majority of red. The second round would get rid of that. We can try it, right? So let me download this one. Okay, so I'll open it up using Paint. And we'll sample again. One 177, 108, 120. That one looks. Let's try it one more time. Yeah. So these are the pixels that are really small now. So 186, 74, 99. Let's try it. Okay, so I can call the function again. Now it's one. What's the color? 86, 74, 99. And the same region. So we can try to run it again. This would hopefully get rid of those shines. And you have to do it several rounds. Let's try it. Jenny, no red. Ooh, we put makeup on her. So it's not the best, as you can see. And so, okay, this is not perfect, but okay, so at least that shine is gone, right? The red shine is gone a little bit. And it's about how do we avoid something like this? You can focus on the individual eyeballs now. Instead of this region, like this region, you can just say, let me focus on this eyeball. This eyeball is between 98 and 104. 98, 104. And y should be 124, 134, around this number. So this is the left eyeball that we'll try to take care of. And then you do the same thing with the right eyeball. If you look at it, this one, I mean, the left eyeball is pretty good now, right? So the right eyeball, you do the same thing. You measure the box you want to put in here, and then you measure the color and change it. So if you're a perfectionist, definitely can do several rounds of function call, and they will just patch up different regions for you. Any other question? All right. So this is the key concept. I think we did this example already. Now, when you try to manipulate pictures, let me see. Before we do this, I want to talk about other effects. Okay, so not only can we do this, there are other effects that we can do. We'll come back to that exercise in a little bit. Slides. So another effect we can do is you can put one picture on top of another picture. For example, you have this bear, you have this caterpillar. I can put the caterpillar on top of the bear. And this is something, it's also related to background substitution. Let me give you a quick demo for this effect. Okay. So first thing, don't forget to import. Okay. So we read in image 1 equals to load image bear.jpg. Image 2 equals to load image caterpillar.jpg. And then I want to put caterpillar on top of the bear. So all I need to do is I need to specify a region that I want to put the caterpillar into. So I want to maybe put it somewhere around here. Okay. So all I need to do is obviously caterpillar should be smaller than the bear. I think they are. So what I want to do is I want to go through the bear. You know what? I want to go through the caterpillar. And then I will copy this pixel to a certain spot in the bear. So I'll say h equals to the height of image 2, w equals to the width of image 2, y in range of h, but j in range of w. I would simply copy this region. So I would copy it image 1, I plus 100, j plus 100 equals to image 2ij. And that's it. So this would copy caterpillar on top of the bear, which is image one, save image one as strange.jpg. If I run this, you should be able to see, unless the dimensionality messed up, the Python demo.py. Yeah, I think index is out of bound. How small is this bear? The bear must be pretty small. Let me see. What's the dimensionality of the bear? The bear is a pretty small picture. The caterpillar is about the same size as the bear. Interesting. Let's take a look at how big the bear is. You would figure the bear is bigger than the caterpillar. Let's look at the information about the bear. Bear is 373 by 373. It's really small. How about caterpillar? Caterpillar is 329 by 329. So it looks like the the bear is about the same size as the caterpillar. What do we do? I would do this. Okay, we can blow up the bear. In fact, we can blow up the bear. We can make the bear twice as big. I think that probably would work. Okay, so this part is not required. Okay, so you don't have to know how to double the size of a picture a picture in here. So let's see. Let's create it. So bigger equals to create image. Let's say the height of image one, the width of image one, the color is all 0, 0, 0, for example, and then we'll double its size two times. Okay. And then I say for I in range of the height of bigger. This is pretty bad code, but we just want to blow it up really quick. J in range of the width of bigger. The bigger ij equals to image one, I divided by two, j divided by two. I think now I have a bigger bear. Save image, bigger bear .jpg. Then this would blow it up twice. Let's omit this part for now. Okay, let's create a bigger bear so we can use it. A typo in here. Okay. All right, so we have a bigger bear. This is the bear. This is the bigger bear. They look the same, but I believe this one is bigger. What's the dimension? Is there a way that we can inspect? I don't know. It doesn't tell us what is the value, the dimension, but it looks bigger, at least from what from what we have before. This is bear.jpg. If I open it up, so this is the original bear, this is the new bear. It looks like it is bigger, right? At least based on, I didn't zoom in, so it should be double the size. So now we are good. So let's forget about this thing. Let's do this thing. So we will load in bigger bear .jpg, and now our code shouldn't give us any trouble. Python demo.py. So this should be a strange bear. Now the caterpillar is sitting on top of the bear, right? This is not a lot of fun, right? Because it looks like it just blocks the bear. So a better way is you can mix these two pictures together. So you say, okay, image one at this location, this thing times. So what I can do is this. Image two is the caterpillar. Image one is the bear. So let's say RGB R1. Let's say R1 G1 B1 equals to image one I plus 100 J plus 100, and then R2 G2 B2 equals to image 2 IJ, and then I can mix them together. I'll say R equals to typecast this into integer R1 times dot 6 plus R2 times dot 4. So it's like I'm mixing 60-40. 60% would come from the original bear, 40% would come from the caterpillar. And similarly, you can do G equals to int G1 times dot 6 plus G2 times dot 4. B equals to typecast into it G1 times dot 6 plus G2 times dot 4. So these RGBs, now you can give it to this bear. So it's an image I plus 100, J plus 100, image 1 equals to this RGB. Now, you won't see this exact like covering in here. They'll be kind of mashed together. Okay, if I run the code and you look at this strange, it's like there is if you look at this one, it looks like there is some sort of watermark with a caterpillar sitting on top of the bear, so it's becomes a little bit transparent. So that's something you can also do. Okay. So this is the part where not only can you kind of put one on top of the other, and you can also mix them together. You can also judge based on the color. There are many special effects you can achieve. Okay. Why did I add 100? So if I don't add 100, I just wanted the caterpillar to be somewhere in this picture. Add 100 is offset 100 by row and column. If I add 200 in here, for example, if I add 200, the caterpillar will be further down. Right? If you look at it, this is the original picture. Right? This is the original picture. And now if I refresh it, hold on. I need to change plus 200 in here too. Okay. Now it should give us the intended result. If I refresh it, you can see the caterpillar is further down compared with before. This is before, this is after. So it just this offset of 200, 100 is to allow you to say, where do I want to put the caterpillar? Okay. All right. So just some special effects. that we can achieve. All right. Let's take a break. Okay, let's take a break. Once we come back, we will get started with steganography. We'll start with this one, and then we'll get started with the steganography. Let's take a break until 12 o'clock. Okay, break time. All right, let's get ready for the second session for today. Okay. So the second session, I think we have one more exercise to go through, and then we'll get started with steganography. Today we'll just talk about the idea of steganography, and then Thursday we'll look at the details of how to implement steganography. Steganography will be the topic for PA for PA5. Okay, for PA5. Let's get started in here. Okay. So this is the code that is fairly similar to how we copied the caterpillar into the bear. Okay. So we have copy region, image, row source, row starting point, column starting point. I think this is the source. Right, it's not starting point. This is row source, column source, row target, column target. We grabbed the image width and height, we created a new picture, and then this is what we did. What does this code do in here? Get rid of that. So based on what this code do, so we load a picture called arch.jpg. We say copy region to new by passing this information. We save image 1, save image 2, save picture as result 3. What would this code do? Would we see an error, or would we see like some duplicates of arc, or a certain region of arc is copied somewhere else? How do you analyze this code? It's more like an exercise for memory model. Okay, so let's vote in. Take your time. Okay. Vote in, please. What would you say this code will do? So a lot of us saying the picture will be changed in some way. Let's check it. Right, let's check it. All right. So how do we do this? Let's draw the memory model, and then probably you'll realize what's going on here. So I've pick equals to load image. So pick is in the global frame, right? So pick is pointing to a 2D list of pixels, and for example, that's an arc. Okay. And then I call this copy region 2. I pass in pick to this image. So there is a new stack frame created. This is the copy functions stack frame. It doesn't have a pick. It has this image. And this image is pointing to the same arc in there. And then I pass in 10. So RS is 10. CS is 30. RT is 50. CT is 50. And then I grab the width and height of this arc. That's something we'll grab it. And then we say create a new canvas. So we create a brand new canvas that has the same dimension as this arc. So there's a new image is pointing over there. So we created a 100 by 100 region. Let's say copying from this source. In other words, this is like 1030. It's like I carve out a box of 100 by 100 from here and copy it over there. That's basically what we are doing. And this target is 50-50, so it's not going to be at the exact same spot. It's somewhere in here. So part of this thing is copied in this new image. In other words, you copy from this region starting at the location 1030, copy it to this region at the location 50-50 as the upper left corner. And the dimension of this region is 100 by 100. And then I save, and then I'm done with this function, right? Once I'm done with this function, this whole thing is done. The first thing I did is save image result .jpg. First thing is, where is image? Image exists in this function stack frame. It doesn't exist in the global frame. So this part would in fact cause an error. So is the second part. The arc is not changed. The arc is not changed. So the answer is A, in fact. Unfortunately, none of us voted for A. Okay. So result 1, result 2, you don't even have access to them. That's why you're gonna see an error in here. Any questions about this part? Why there's error? Because you're trying to access image and new image in here. Once you finish the function call, this part is done. You can save them inside the function. That's fine. But you can't use these image, new image after the function call. Okay. Any questions?
How do you like fix it?
I said you can copy. Let me. You can copy these two lines inside the function. Let me just give you a quick demo here. Okay. So how do I fix it? This is demo. No, this one is have to copy in the pictures. I don't want to do that. I'll paste in this code that we just had. I'll change it. So everything here should be tabulated in. Everything here should be tabulated in. Everything here should be tabulated in. And then just have to have this result. So if you run this, let's call this bear. How about bear? We have the bear. So if we have this thing, we're in trouble because these two statements will give us errors. You see, well, this one is not defined, right? You start from this line. The way you can do it is you can save it in here. You can use these variables inside the function, and it's fine. This would save the pictures. If you look at, you have result 1, result 2, result 3. Result 1 is still gonna be the bear. Result 2 is gonna be a black region, but only this part of the bear is copied in. If you look at it, only this region from the bear is copied in here. Result 3 is still the bear. That's how you can change it. Any questions about this part? Again, this has something to do with the memory model. Okay, you cannot access things that that doesn't belong to your frame. Okay. All right. One other change. If I add return new image, if I simply add this return new image in here, what is going to happen now? The same code in here. If I say return new image, what do you think would happen now? Can we vote again? What's going to happen if I say return this image? All right. So we'll stop the vote here. I think we're doing better. At least some of us are still, well, it's still gonna cause error, right? Even though you return this thing, it doesn't mean, like when you say return new image, what is returned? You don't return this thing. You return the arrow from new image. And in here, I never saved it. I never save it. So even if you return new image, this part would not work. And besides, this image was never visible inside our global frame anyways. So this first line would still give us error. And even if you say I remove this line, it's still gonna be an error. Okay? Let me show you. So if you have these things in here after the function, and you say in the function, you say I will return new image. Even if I say I don't save result 1, now you say you return your image, now I can use it, right? The answer is no, you still can't use it. Because returning something doesn't mean that you have access to it now. You need to capture the return value. If I now run the code, you're still gonna say new image is not defined. So how do I make it defined? You can say I'll have for example result equals to this, and then save my result here. So this new image, whatever the arrow it is pointing to, will be given to this variable, and this variable can be saved. If I do something like this, there won't be any errors anymore. There's no more errors. And result 2 would be the answer in here. So result 2 would be just like this. Copy part of the region. Okay. Memory model is basically in your mind, you basically become a human computer, right? We're trying to ask you to understand when computers run your code, how it is going to execute your code. It's a very important thing, right? If you say I'm a programmer, but I have no idea how my code will run, it won't work, right? You must know very, very clearly how your code is executed, so you can write your code correctly and efficiently, right? So memory model is important, and it is confusing, right? Because it's different from how humans work. Just remember, computers are not humans. They follow predefined rules here to the bone. Okay, so they don't make any variations. When you say return something, what does it return? When you pass something to a function, what is passed? It's always by value. You never return the objects that you have. These are the objects. You never return them. You all the time you pass these arrows around. You pass these values around. That's it. Okay. Are there any questions for this exercise? Now, let's look at steganography. Okay, I think today we can get into a big part of it. And once we finish this entire slide, we can call it a day. And then on Thursday, we should be able to finish the rest of steganography. Okay. So steganography is the last topic for image processing. This is the last concept we'll cover. Okay. The reason why we want to cover this thing is number one, it is interesting. Okay. Number two is it kind of shows you some sort of bitwise operations, which I think is useful for your future classes. Okay. So by definition, what is steganography? Steganography is basically you want to hide some. Excuse me. You want to hide some information, but instead of putting that information secretly, you just kind of show people that information just right in front of their face. But unless they know where to find out those information, they cannot see what you're trying to say. Okay. So the old school steganography is something like this. You may have a sentence, right? Kathy saw 8 airplanes penetrate the skies aloft, 7 would really keep straight. What does this mean? It's just a silly sentence, right? But we're trying to hide some information in here. If you look at the first letter of each of these words, ROCKS, so basically CSE 8A, PSA 7 rocks. In fact, in a regular quarter, PA 7 is the steganography assignment. So for us, it's PA 5. The idea is, if you don't look at the first letter in here, it is very hard for you to decipher what we are trying to say. And the information is right in front of us, but it's hard for us to see. Okay. So steganography is more about hiding information in plain sight. And we can do the same thing, like we hide these words in the sentence. We can also hide a picture inside the picture. So I have a picture, I want to hide it. But I want to hide this picture in another picture. And then I kind of send that picture around, but no one can see it. That's the goal. Right? That's the goal. So how do I do this? The fundamental rule is the following. Human eyes are not perfect. In other words, if I tell you this, okay, so I have blue pixels. These are two blue pixels. One of the blue pixel has the RGB value 395611. The other is 3759 100. Can you tell which one is which? The RGB values is slightly different, and I have these two blue pixels. You can stare at whole day. Most likely, regular human beings can't see it, right? Unless you have some special power, which is possible. But human eyes cannot see the variation of these two pixels, right? So what does this tell me? It basically tells me if human eyes cannot tell these two pixels apart, and these two pixels indeed they are different. Maybe I can, excuse me, maybe I can change a pixel from a picture just a tiny little bit. For example, I change from here to there. Human eyes won't be able to see it, and this change would be the information I want to hide in that pixel. So it may work. Okay, I remember this is a real case. I think there was a spy from China. He was working in one of the companies, or she, I don't know. But what they were trying to do is they were trying to send the information back to the agency in China, and that person posted a picture on his or her own website, and that picture, in fact, has the information that they want to share back to China. And I think the FBI or CIA, whatever, they were able to decipher the image and figure out what's going on. That's kind of a real world application of steganography, right? So you can share a picture without other people knowing around what is hidden in there. Just for example, I may be sharing this picture around, it's just the engineering bear, but I may have a hidden sentence in this picture. Right? That's something we can, if we have time, we can do a quick demo today. Okay. Although I can't show you the code, but maybe not today, but on Thursday we can do a quick demo. Okay. So that is the idea. Change the pixels a tiny little bit without human eyes recognizing it. But obviously, if we use machines to examine the pixels, the machine will be able to tell the difference. Okay. So in order for us to change these values a tiny little bit, it is better that we look at these RGB values in the binary format. The reason why we would like to examine them in the binary format is, number one, that's how these data are stored. Number two is if you express the number in a binary format, you can control the variation on the pixel in a more refined way. Okay. So that is the goal. Okay. Let's look at some examples, like how do I convert a number into binary, and then I will show you how to use Python to do this. Okay. So you will learn more about this binary representation in CSE 30 if you want to take more CSE classes. But the idea is normally humans deal with base 10 numbers. We can convert base 10 into binary by simply dividing this number by 2. Okay, so for binary representation, you only have 2 possible digits, either 0 or 1. Right? So 39 divided by 2 is 19. You write the remainder here. 19 divided by 2, you get 9. 9 divided by 2, you get 4, remainder 1. 4 divided by 2, quotient is 2, remainder 0. 2 divided by 2, quotient is 1, remainder 0. 1 divided by 2, quotient is 0, remainder 1. And you write it out in this way. It'll be 1, 0, 0, 1, 1, 1. This is the binary equivalency of 39. Okay. So how do I know this is right? For binary digits, just like in decimals, like for example, 39, you say the last one has a weight of 10 to the power 0, this one has a weight of 10 to the power 1. So it's 3 times 10 plus 9 times 10 to the power 0 is 1. So it's 39. In here, the powers becomes 2. This is 2 to the power 0, power 1, 2 to the power 2, 3, 4, 5. So this value is 1 times 2 to the power 5 plus 1 times 2 to the power 2 plus 1 times 2 to the power 1 plus 1 times 2 to the power 0. This is 16. No, it's not 16, it's 32. 32 plus 4 plus 2 plus 1. I think this equals to 39. Right? So that's the binary equivalency of 39. We just convert it into binary 1, 0, 0, 1, 1, 1. We say this bit is the most significant bit. This bit is the least significant bit. What does it mean? It means this bit is the most important bit to help us determine the value of this binary number. This last one is the least important. In other words, if you mess up the last bit, the value will be incorrect, but not by a ton. If you use the other one in here, if you mess up this one, the whole value will change a lot. Okay, so this is the most important bit. This is the least important bit. And in general, the bits on the right side in here are less important than the positions on the left side. Any questions about how to convert decimal into binary? All right. Now, to go from here to binary, like if I want to convert 5611 to binary, I'll give you some time. Can you do this by yourself? Just do along. You can pick either one, either 56 or 11 into binary. The 11 is 101. Okay. You can pick either one and convert it into binary. You try to do the math and vote in once you're done converting by hand. You only need to do this once, right? So this is not something super important. It's very mechanical. right. Um, let's look at this one. Okay. Um, so I'm pretty sure you all have tried this, right? Let me show you how to use Python to help us. Okay. So here's the code. You don't need to write the Python code. You can just use the Python shell here. Clear it. So some of you ask me, hey, what's the difference between Python file name or Python-i a file? For example, if I say Python-i demo.py, I would end up in Python after I run this code. If I simply say python.py, I'm back to the shell. I don't stay in Python. So that's the only difference between them. So let's say I try to get into Python, and what I do is I'll say, I have a 56. Can you convert it into binary? All you need to do is call this bin function. Bin 56, it tells me 0b 56 is 111000. That's it. Okay. So this is one of the things about binary. Now, so what's a binary of 11? That's 11. So you can easily change any number into binary, right? So 0b is the prefix. Now, so what if a binary I want to convert it back into decimal? Like I would say 0b 111000. This would simply print out the decimal equivalent of this binary number. If you add a 0b to a number, that basically tells the machine, okay, I'm writing out this number in the binary format. So it's fairly easy for you to go between binary and the decimal. You can just use Python to do it for you. Any questions about using bin to convert decimal into binary, and use prefix 0b to express a binary number? And by default, Python always display things for us in decimal. So if you simply say, you can also assign a binary value 0b1100 to a variable. So what is value of x? X is 12. Okay. That's kind of what we have. Any questions? All right. So this is kind of just a basic conversion in here. Now, a few things that we want to observe, okay? Because we need to manipulate binary numbers. So number one, what is the maximum amount we can change a value in decimal by changing the two least significant digits in, this is in binary. So the two least significant digits in binary. In other words, if you have like a 0b110011, if I look at the last two bits, if I change the last two bits, what's the maximum amount of change I can inflict on this original number? Okay. Is it 1, 2, 3, or 4? Let's do a quick vote. So let's check, right? We'll stop the vote. A majority of us said C, 3. Why is it 3? Because if you think about the biggest change I can change from this one is 1100. I change 11 into 00. That's the largest amount of change. 11 in decimal is 3. This is 0. So the biggest amount of change is to change from 3 to 0, which is 3. So what does this mean? If you look at the value, okay, let me write it in here. So if I say, let's try it. I have a value x equals to 145. Okay. And so what's the binary equivalency of 145? It is this thing. As you can see, the last two bits in here is 0, 1. If I just change it, the maximum amount of change I can have is I can't flip it, right? So I have 0b, 1, 0, 0, 1, 0, 0. Now the last two bits. From 0, 1, how about to 1, 1? This is 147. So if I make this 147, right? Now, if I say, how about 1, 0 is 146. How about 0, 0? It's 144. In other words, if you look at these four values, the only difference between those values are the last two bits. The range in here is 144, 145, 47, 46. So the maximum difference that I can see is to change between these two numbers, which is 3. So if you mess up the last two digits, the amount of change you can inflict is at most 3 in decimal, which is very small, right? Which is very small. Any questions about this? Now, how about I mess up the last three digits? What is the maximum amount of change I can expect? Vote in whenever you're ready. What is the change? The maximum amount, I think we got this one. Okay. We'll stop the vote. Is 7. So in other words, if I mess up the last two bits, the last 3 bits, it's not gonna be something that human eyes can tell the difference. If I think about the RGB values are these values, right? So in essence, the conclusion is we can do whatever we want to do with the last 2 bits, or potentially 3 or 4 bits. So for example, if this is 39, 56, 11, if we express them in binary, this is what we have. And I just kind of change the last 3 bits a little bit. Everything else in the front are the same. This is 32, 61, 98. Human eyes cannot see the difference between these two colors. Okay, let me show you. Let me drag this out. Okay, I want to create 2 pictures, and you tell me which one is this one, which one is the other one. Okay, I'll create 2 pictures, and I'll save it. So image 1 equals to create image 300 by 300. The RGB value is 395611. This is the first one. Okay. Image 2 equals to create image. Also a 300 by 300 picture, but each pixel in there is 32, 61, 98. And now save image, image 1, and I will say something. And then save image, image 2, another thing. Okay, let me run the code. I'm doing this intentionally not on the screen, because I want you to see the result in here. All right, so this is what we have. I have two pictures. One is called T, the other is S. Let me show it in the new tab. I want you to tell. I press the wrong button here. Let me see. Hold on a second. I think I pressed the power button as I'm trying to adjust. There we are. All right. I think I may have to reshare my screen. Hopefully, this one. Okay. So now I have two pictures. One is like these two. Can you tell them apart? I think it will be very hard. Can you tell them apart? Which one is 39, 56, 11, and the other one is 32, 61, 98. Which one is which? At least I can't tell them apart. And I basically blow up this pixel 300 times for us to see the difference. If you reduce them by 300 times, I don't think any human eyes can tell the difference. Yeah. In other words, these two pixels, they're almost identical. If I mess up the last 3 bits, and this would help us to hide the information. In other words, if I just change the last 3 bits of pixel, and this is the information I want to hide in there, I can perfectly hide those information in there without other people seeing it. Okay. Any questions? This is the last vote in here. Then I can do a demo before we call it a day. So let's finish this exercise, then we'll take a break. Okay. So number one, if I use 8 bits per color channel, 8 bits in binary, okay, how many different colors does 8 bits per color channel allow us to represent? How many different colors? So 8 bits in here, 8 bits in here, 8 bits in here. What's the total number of colors we can represent? Let's do a quick vote on this one. All right. We'll stop the vote. The majority of us voted for C. That is the correct answer. Because for each color channel, each color, like for example, for red, you can go from 8 zeros to 8 ones. This is decimal 0, this is decimal 255. So you have 256 unique levels of red, and then you combine that with 256 unique levels of green and 256 levels of blue. So that will be 256 cubed. So it's about 16 million. That's a lot of colors for us to represent. Okay. So that's kind of that's why the picture we look at normally is pretty good. Okay. And we may have to reduce that a little bit. Hopefully this would not mess up too bad, but we'll see. Okay. So let's take a break. Okay, take a break, come back at 1 o'clock. We'll finish this exercise and then we'll do a demo. That'll be it for us today. Okay. So take a break, come back at 1 o'clock. Everyone, take a break. All right, everyone, let's finish up the last session for today. Okay. All right. So for this one, we have the last 3 questions, right? Now, if we use 2 bits per color, like instead of 8 bits per color, if we use 2 bits per color, how many possible values can I have for each color channel? So how many possible colors I have per color channel? In other words, if red, we have 2 bits. How many colors can I have for red? How many levels can I have for red? You can vote in whenever you're ready. Okay. Right. This is per color channel. Per color channel. Okay. All right. Let's look at this one. Okay. A lot of us said 64. 64 is the total number of colors we may have. But if you say per color channel, that's 4, right? Because you have 0, 0, 0, 1, 1, 0, 1, 1. So you have 4 levels per color channel. And since you have 3 color channels, 4 times 4 times 4, that's 64. So the correct answer, in fact, would be C. But if you said 64 means that's the overall total number of colors you can represent. Why do I care about this? Because once we start to hide information using pictures, then the excuse me, the extracted information later on would lose some precision. In other words, you're gonna have a picture that is gonna be different from the original picture. Okay, that's kind of what it is. Any questions about this? So 8 bits per channel, nice. 2 bits per channel, 64 colors is okay. It's like the picture is painted using crayon instead of like a realistic picture. Okay. Now, if I use 2 bits per color channel, what should this color be in theory? RGB. Let's vote in. Okay. What should this color be? All right. So a lot of said it's pinkish. That is correct. Right. You have a lot of red, no green, a little bit of blue, and you mix them. It's kind of pink color. Right. How about if I write this one in Python? If I say 110001, what do you think this color will be in Python? Let's vote in. This will be the last vote. We're going to finish fairly early today. What will be the color for this one? If I do it in Python. And I'll give you a quick demo of this one. All right. So let's stop the vote. We disagree. Some of us say, oh, this is going to be pink, this is going to be black. So those are the two popular choices. Let's analyze this together. That's not what we have. Where's that? Add that here. Okay. So let's do a color demo here. You know what? I'll just use this one. So if I say, let me create a picture of color 110001. Right, this is the color we want to have. So that's the RGB value, and then I can save image. If I run the code, I'm gonna see a test.jpg. No, oh, sorry, image one. So test.jpg, if you look at it, is pure black. This is pure black, right? The reason is simple, because 0B11, this equals to 3. So we are basically looking at a pixel 301. That is basically almost identical to black. If you say, I really need to make it a pink, you make sure that they represent the more significant positions in here. Because Python always use 8 bits per channel. So if you simply say 0B11, it's going to assume it's this thing. If you really want 11 to give you the right color, you want to append the zeros yourself, 6 zeros. You append 6 zeros in here. You append 6 zeros in here. And now if you run it, your test of py will be pinkish. Okay. Any questions about this part? So this picture would still only have 64 different colors, but at least the colors are what you want instead of everything being black. Okay. Now a quick demo in here, and then we'll call it a day today. See, this is one of the pictures that I modified before. This is from a class. Let me see. Let me give you a demo in here, okay? Yeah. Let's do this, okay? So I have Paint, right? Let me create a new file. Save. So let's say resize it. Let's resize it, not too big. So let's say pixels. Let's say it's like maybe 100 by 100 pixels. All right, so this is the picture. And I'm gonna write something in there. I'll just write today's date. Right, that's the secret I want to put. Let me save it. I'll save it here in my test, and then I'll upload it. So I'll call this secret.jpg. All right. Now I will upload it to our ad stem. Where's secret? We should have secret here. So let me delete. We have so many pictures in here. Okay. Oh, I also deleted the secret. I have to upload it again. There we go. Okay. So I want to hide this thing inside the bear, for example, without you knowing that it is in here. So how do I do it? I basically, the idea is I would grab the last, so I'll go through this picture. I would go through every pixel in this picture. I would basically grab the most important information of this picture for every pixel, and then put it in the least significant positions of every pixel in here. And that would allow me to hide the information. Okay. As for how do you do it, we need to talk about it on Thursday and see if there's a easier way for me to change it. All right. So I will use the brute force way. Okay. So this may not work well. Let's see. So I'll have a, for example, secret equals to load image secret dot jpg. And then the bear is like my, we call this the context image, which is like the picture I send around. So context equals to load image bear.jpg. Okay. So this is what I'm gonna do. I'm gonna do this thing. This is different from how you're gonna do it in the homework. I'll give you a kind of a more detailed demo because it's the homework. I can't show you the code, But I'll show you the ideas in more detail on Thursday. But today I'll just give you a very kind of a brute force way for you to do it. Because our secret is black and white, I think we may be able to do it. I'll go through the secret. Say, height equals to secret, the height of the secret. Width equals to the width of the secret. And I'll go through. Excuse me. Of I in range of H for J in range of W. Sorry about that. So I'll grab the RGB value from the secret. And then I will just grab the most important digits in decimal. So for example, if I have a pixel of if this is a pixel, what I will do is how about I just grab the leading positions. So this will be 2, this will be 0, this will be 1. That's what I want to have. So I'll say important are equals to R mod 100. This will give you the 100th digit. Or not mod 100. Divided by 100. G1 equals to G divided by 100. B equals to B1. So I extracted this information from a pixel in secret. Now I will put it in the last position of the corresponding context. Let's see. I can reuse RGB. I say RC, GC, BC. So now I see RC equals to RC. I want to get rid of the last digit, so a little bit of math. Okay. Mod 10 would be the last digit. RC minus it, plus R1. And similarly, GC equals to GC minus GC mod 10. This would basically clean up the last bit in binary, in decimal, plus G1. Now I've put the secret, the most important part of secret, into the least significant part of context. Now I'm ready to save it into this pixel. I will save it. Okay, so I'll save image, context. Let's say this is the encrypted .jpg. Let's run it. So my context used to be bare, and now my encrypted is this thing. Can you see any difference? Well, at least I don't think I can see any difference. If you look at these two pictures, they are almost identical. Right, they're almost identical, but they are in fact different. Now, how do I recover the original message? If you want to recover, all you need to do is to say, let me load, say, this is the part to recover the image, recover the secret. In other words, I will send this encrypted.jpg picture around without people knowing, oh, it looks like just like a bear, but it's not, right? So there is this state that is hidden in there. Let's see if we can recover it. So it's going to be pretty tricky for us to recover it, but we'll see. Okay. Hopefully it will work. First, I need to load the recovered image. I would say, sorry, I will load the encrypted equal to load image encrypted.jpg. So I'm the receiver. I got this picture. Now I'm ready to say what is going on. I have no idea where this secret message is in this pair. It may be somewhere here, maybe somewhere in there. So I have no idea. I just have to go through the entire picture. Okay. So what I will do is I would create result equals to let's get the width and height of the encrypted image. Result, I create a blank canvas, create image with this same height, same width, and I'll just make everything is white to start with. Okay. Now I'll go through this picture for I in range of height, for J in range of width. I would grab the RGB from the encrypted IJ. And now I need to extract the least important bit, the least important position. So all I need to do is I say R equals to R mod 10. This will be the least significant digit in decimal. And then I just multiply this with 100. G equals to G mod 10 times 100. B equals to B mod 10 times 100. Again, these approaches will be explained in more detail. But we're just extracting, like, for example, I'm having 256, no, not 250, like 112, 97, not that, 91, and 40, for example. I basically want to change this into 200. I want to change this into 100, and this will be just 0, 0, 0, 0, which is just 0. That's what I'm trying to do here. And then I say result ij equals to RGB. And then I can save the result, say image, I'll say result, and I'll call this decrypted.jpg. We'll see if it works. Okay. What is going on? Encrypted. Oh, I have a typo. Well, the file name has a typo. Just encrypted. All right. So this is the original secret. Let's look at decrypted. This is what the decrypted picture look like. As you can see, this is different from before, but you can clearly see there's this state hidden in this picture, in the bear, in this bear. on the upper left corner, but you don't see it. You don't see it, right? As from the human eyes, but we can write a code that actually can decrypt here. Any questions about this demo? As how do we do it? This approach is not as good as what we will discuss on Thursday. But I just want to give you a sense. You have a secret picture. You hide it in your context picture in a certain region. We assume the context is bigger than the secret. And then once you have this encrypted picture, human eyes can't see it, but you are able to recover it. You're able to recover it using the decryption to get back this decrypted picture. This decrypted picture will be different from the original picture, but hopefully human eyes can still see the difference. Okay. Are there any questions about this part? If there are no questions, I think we can call it a day today. We finished a little bit early today. That's fine. Okay. If you have questions, I'll be happy to answer them. But other than that, we are done today. Okay, everyone. Yeah. Thank you.